My invisible friends, hello and welcome back to our series on electrical and computer engineering. Our conversation tonight is about how to include inductors and capacitors into our circuits. In a previous video, in a previous movie, in this very same series, the one on circuit elements, we have seen that the behavior of an inductor is given by a differential equation. V is L di dt. And that the behavior of a capacitor is also given by another differential equation, I is C dV dt. So it makes sense that if we include inductors or capacitors into a circuit, the behavior equation of that circuit will become differential equations. But fear not, very often we don't really care about finding the solution for that differential equation. Sometimes we do, and I'll show you how, but very often we don't. We only need to find the differential equation because that equation per se will give us a lot of information about the behavior of that circuit. You don't believe me? Let me give you just a couple of examples, not proof. A simple RL circuit and a very simple RC circuit, and then we will talk again.
Let's consider this very simple circuit with one resistor and one inductor. The current in that circuit, this one, happens to be the current in the inductor IL. That current will produce a voltage drop in the resistor given by Ohm's law, Ri. The same current will also produce a voltage drop in the inductor with that polarity and with a value given by the behavior equation of the inductor L di dt. So we are ready. We can write a KVL equation around that loop, and I will do that counterclockwise beginning on the right bottom. Going up through the inductor, we raise a voltage L di dt, and then we are at the top right corner of the circuit. We continue to the left and raise the voltage by Ri volts, and then finally, following through the voltage source, we go down by Vs, and that's equal to 0. That is Kirchhoff's voltage law. Let me move the value of the voltage source over to the right, and what have we got? We have a first-order differential equation whose solution is the current in the inductor. Just what I told you. Include an inductor in a circuit, and all of a sudden the behavior is given by a differential equation. Another example, a simple circuit that has one resistor and one capacitor, an RC circuit. Allow me to use M&A this time. I'm choosing this reference node and this node on the top of 1. I'm promoting a binary node to the status of true node, node 1. The branch currents I choose arbitrarily, one entering node 1, one leaving node 1. Please observe that the voltage of node 1 in reality is also the voltage in the capacitor, right? V1 is Vc. And the current in that capacitor is given by the behavior equation of the capacitor is C dVc dt. But Vc is V1, so the current in the capacitor is C dV1 dt. We are ready. Let's write a KCL equation for node 1. Current is going in, V of the source minus V1 over R. There you go. And that's equal to the only one current leaving the node, the current in the capacitor that is given on the top right, C dV1 dt. V1, we said, is just the voltage in the capacitor Vc, so the equation can be written like so. Now let's multiply both sides by R and move negative Vc over to the right-hand side, and then we flip the equation, and what have we got? We have again a first-order differential equation whose solution is Vc, the voltage in the capacitor, as a function of time. That is an RC circuit. So you see, as I've told you, include a capacitor into a circuit, and all of a sudden, the behavior of that circuit is described by a differential equation.
So now you believe me that we need to find differential equations of circuits, huh? Over the years, I found that one of the easiest and most powerful ways of finding that differential equation for complicated circuits, not for the simple circuits that I've shown you, is by utilizing the powerful Heaviside differential P operator. Hey, don't be scared. So that differential operator is simply this one. You and I have grown used to seeing differential equations like this one. In there, we are using Leibniz notation to represent the differentiation of the function of time y. But using Newton's notation, the same differential equation would look rather like this. It's the same equation. In both of them, we can identify the order, second order. On both of them, we can identify the three coefficients of the differential equation, and we can identify the right-hand side of that differential equation. Let's present a new notation that will prove to be extremely useful to us electrical engineers. The P operator introduced by Oliver Heaviside. Leibniz is utilizing a very convenient differential operator, d over dt. But Oliver says, how about we use instead a simpler operator? Instead of d over dt, we just use P, meaning exactly the same thing, so that whenever we see dy dt, the derivative of y with respect to time, where y is a function of time, we write it just simply P or y. And the second derivative of time of y? Well, P squared y. And the integral of y with respect to time? Y over P. It is just a notation, but a powerful, simple, and elegant notation it is. If we apply that notation to the differential equation we saw before, it becomes this one. Nice, eh? If we factor out the function of time y, the same differential equation becomes this one. If we make a bold move and divide both terms by the differential operator, we get this, which is not a solution, mind you, far from it. It is still the same differential equation written in a different way, a very convenient way that we will find in many electric circuits. But still, that is just a differential equation. In it, we can tell what is the order of the differential equation. Second order. We can tell the three coefficients of the differential equation. You see them in the denominator? You can tell what is the right-hand side term, which is on the numerator. And isolated is the function of time, a voltage or a current that we need to solve for, y of t. No solution, just another way of writing the same differential equation. You say, hey, what do you gain with it? Hold on a second. Let's apply the P operator to two differential equations we have seen a lot before. The behavior of an inductor, V is L di dt. Let's apply the P operator to that. What does it look like now? Oh, it looks like V is LPI. Okay, put that in memory up there. Let's apply the P operator to another differential equation you and I have seen. The behavior of a capacitor I is C dV dt. Right, that would be I is Cp V. Let's divide by Cp both sides of that equation, and it says V in the capacitor is 1 over Cp times I. And for the resistor, nothing new. For the resistor, V is Ri. Let's put those three equations together. Inductor, V is Lpi. Capacitor, V is 1 over Cp I. And for the resistor, V is Ri. If we call Z Lp for the inductor, 1 over Cp for the capacitor, and R for the resistor, we can write for the three of them that for either of those elements, V is Zi. Z, what are the units for Z? Well, think. Amps times Z is volts. The units of Z? Ohms, of course, right? You think, oh, this Z is like sort of a super resistance of the element? Kind of. We could think of it as the Heaviside P resistance of each one of the elements, but that is a very long name. we need to think of another word in English that represents resistance, represents opposition. Another word is to impede. We call that the impedance of the element. So the impedance of an inductor will be LP. The impedance of a capacitor will be 1 over ZP. And the impedance of the resistor, just its resistance. The three of them are given in ohms. It's time for a tutorial to show you how this will simplify our task of finding the differential equation that will give us any voltage or any current in any linear circuit that has inductors and capacitors. Tutorial time.
Before we get into a tutorial time, let's review the essence of what we've said. For an inductor, V is LPI. For a capacitor, V is 1 over Cp. For a resistor, V is Ri. In either of those cases, if we call those LP 1 over Cp and R impedances, then V is Zi, and that is what we've called the general Ohm's law. With the definition of impedance, we have a general form of Ohm's law for any element with an impedance Z, and using the water falls from the sky rule, which is we will assume the current flowing from high volts to lower volts through an impedance Z, any impedance Z, V is Zi. That is the general form of Ohm's law. Now, what are the units of Z? We've said it's ohms. Let's revisit that because students in my class very often ask me this question. We said V is Z high. Volts are Z times amps, ergo Z has to come in ohms. Right, but students still insist. Is that so for LP and 1 over Cp? Are those ohms? Really? Yes, indeed. Z comes in ohms because P, remember, by definition is d over dt, that is 1 over second. So that means that for LP, for an inductor, what we have is Henry over second, that if you freeze the movie, you can see it's ohms in this sequence. And for the capacitor, 1 over Cp is in reality seconds divided by farads, which is ohms. Now, let's proceed. Impedances can be combined in series or in parallel. Really? Really? Check it out. Because impedances, the way we've defined them, they follow Ohm's law, the general form. And because we never abandoned KVL or KCL, that means that we can simplify impedances in series or impedances in parallel exactly the same way that we simplified resistors in series or resistors in parallel. Isn't that something? Not only that, because those three laws, Ohm's law, KVL, and KCL, are the foundation of every solution method for circuits. M&A, nodal analysis, loop analysis, mesh analysis, cut-set, anything. I prefer M&A, you know that. We can use M&A, we can use any solution method of our choice. Let's make a parenthesis here. I will be using the HP50G, whose emulator is free on the internet. You don't have to pay a cent for it to simplify circuits and to find the solution that I'll need. You can use Wolfram Alpha, you can use Maple or Mathematica of your choice. It doesn't matter. Do it by hand. Let's see how we can put two resistors or impedances in parallel using the HP50G, and then we continue with the tutorial time. Observe, in the calculator, I have put the resistances 7 ohms and 5 ohms on the two lower levels of the stack. How do I compute the parallel of that? Well, the first thing I do is I click on the invert key down here. That is invert of 5. I swap those two values with this key. And then again, I click on invert, like so. I add them together and click invert once more. That is the equivalent resistance of 5 ohms in parallel with 7 ohms. So, of course, that is a symbol. If we click on, let's say, evaluate, we will get an evaluated simplified version. By the way, let's review the steps to put those two resistances in parallel. Invert, swap, invert, add, and invert. If only we could make the calculator memorize those 5 keys in that order to be executed at our command every time we need to connect two resistors in parallel. We shall see it works also with two impedances in parallel. That would be wonderful. So that's what's next. How to program your HP50G to learn that very small sequence of instructions. If you want actually that value as a floating point number, you redshift and num, and gives you that the parallel of 5 and 7 is 2.92 ohms. Let's have a look at how we program the calculator. To create a program, we open a pair of chevrons, redshift, chevrons like that. Whatever we type in there will be memorized in sequence. Press inv, the inverse key, and then we write swap. We can find that swap instruction. Inverse key again, we type it, it's memorized. The addition key, it's memorized. And the inversion key, once more. Press enter. And that sequence, which is now a program to be memorized, is on the stack. Now, in apostrophes, I'll give it a name. RPR, resistor in parallel with resistor I. You can call that Z, PZ if you want to. Enter. The program is in level 2. Wait a minute. Yeah. And the name is in level 1. If I press store, it stores what it's in level 2 and level 1. And now I have a program with the name RPR assigned to the letter F1. Every time I press F1, it will execute those instructions. Observe, I'm entering 7 and 5. I press the key F1, bam, and I get the solution. Of course, we could have programmed, turn that into a floating point number or simplify the fraction, whatever you want, but I prefer to have it like that. And that's how I program the calculator to have one key to connect two resistors or two impedances in parallel. Now we proceed with the tutorial time. These 4 different impedances, let's compute them separately. For the first one, a 2 ohm resistor in series with a 3 Henry inductor. The first thing is replace them by their impedances. 2 is 2, and 3 Henrys is, of course, 3P. We add them together. How? As we would resistors, we add them together. The impedance of that branch is 2 plus 3P. The next one, this other exercise. 2, we'll replace that with 2. It's just that impedance. And 3 Henrys, it's 3P, the impedance. We connect them in parallel and simplify as if there were resistors. Like this, 2 and 3P. Connect them in parallel. We have that key down here. Remember, we programmed it. Click, and that is the parallel of those two. If I press the eval key, it simplifies that. That is the impedance of that combination. 6P over 3P plus 2. Check it out. That's what it is. The impedance of this third branch, well, we obtain that first replacing them by their impedances. 2 is 2, and 5 farads is 1 over 5P. With a calculator, 2 and 1 over 5P. Add them together, eval to simplify. That is the impedance. 10P plus 1 over 5P. Check it out. And the last one. Replace 2 by its impedance, 2. 5 by 1 over 5P. And use a calculator to connect them in parallel with this key down here. Simplify 2 over 10P plus 1. That's how we can simplify elements in series or in parallels that are being represented by their impedances. Now we are ready to do something more interesting. Tutorial time 01. That is a circuit. In the circuit, we're given those values. One source, 10 volts, a switch that is about to be closed, a resistor, 2 ohms, 3 ohms, another 5 ohms, 2 Henrys inductor, and 3 farads capacitor. The first thing, of course, is to replace inductors and capacitors by their impedances, right? Absolutely. We want to find what is the current in the source I. Suppose that. IC, well, we'll see what that means in the next movie. The first thing I said is replace everybody by their impedances. 2P is 2 Henrys, And this is 3, and the capacitor 3 farads become 1 over 3p, and 5 ohms is 5 ohms. Doesn't change. Let me move this circuit over to this corner so that I can work more easily. Don't forget that what we're trying to find is the current in the source. How would you find it? Well, if those were resistors, right, it would be easy. I would just find the combined resistance of all of that, the equivalent resistance seen by the source, divide the source value by that resistance, and that would be that current. Well, guess what? I will do exactly the same. Let me find the equivalent impedance seen by the source. The first one, 3 and 1 over 3p. The branch in the middle. Add them together, right? Enter 5. Put them in parallel with a key, RPR. Good. And now 2 plus 2p. There, 2p. Addition, and then I have the complete impedance seen by the source. With the eval key, I can simplify that expression. That is the combined impedance seen by the source. If I type 10, swap, and divide 10 volts by that impedance, I get the current. Evaluate to simplify. What I've got is the current, not really. What I have is the differential equation that when we solve, we get the current in that source. But that is exactly what I want. Let me copy that over here and then write it in an expanded form like so. Let me use Leibniz notation. That's right. What is this term on the right? 240 times d over dt. D over dt of what? Well, of 1. That is the derivative with respect to time of 1. I don't write the 1, but it's there, right? But the derivative of 1 with respect to time is 0, because 1 is a constant. So all I'm left on the right-hand side is 10. That is the differential equation that needs to be solved if we want the current in the source. See, all of this was to find the differential equation whose solution gives us the current that we want. I could have been finding the voltage in the capacitor or the current in the 5 ohm resistor or anything else. The process is the same. Tutorial time 2. A more interesting, more complicated circuit. This time we have the same 10 volt source, but we have many more resistors, and we have 3 inductors and 3 capacitors, right? Right. What is the first step? You know it. Replace every inductor and every capacitor by the impedance. Fine. So 10 volts, 2, 3, 5, 2, 3. The resistors and the source, they remain. But instead of 2 henries, we have 2p. Instead of 1 farad, I have 1 over p. 2 henries, 2p. 2 farads, 1 over 2p, and last 3p and 1 over 2p. Let me move over to the corner of the circuit so I have more room to write equations. That is the circuit. What is the question? The question could have been anything. In this case, to make life simple, let me find what is the current in the source as a function of time, or rather, let me find what is the differential equation whose solution is the current in the source as a function of time. How would you do that? You can do it any way you want. But in my case, because it's simpler, I will find the equivalent impedance seen by the source and then divide 10 by that. And that will give me the current in the source, but rather it will give me the differential equation whose solution is the current in the source. Let's see. Simplifying. This branch, this one here, 3p and 1 over 2p. Those 2 branches in parallel, right? 3p and 1 over 2p. Connect them in parallel with RPR. And then add 2 and 3. Yeah. Let's make sure with mode and CIS that all those radio buttons, numeric, approx, and complex, are cleared. Otherwise, this is not going to work. You know that. Well, 2, 3, and this impedance. Addition and addition, we have the impedance of the whole group on the far right. And then let's get to the branch in the middle. 3 and 1 over 2p, these 2. Put them in series. Addition, that's fine. And then this one, 1 over p and 2p. Put them in series. And now what? And then put those 2 in parallel with RPR. Parallel. Fine. And then 5, we add 5. And then put that in parallel with the previous value that is in level 2. In parallel. And then add 2 plus 2p, like so. Yeah. Let's add them and simplify. That's right. That is the equivalent impedance seen by the source. Let's divide 10 by that. 10, swap, divide. That is the current in the source. You say, no, that is not the current in the source. It's not. What that is the differential equation whose solution is the current in the source. What is the order of that differential equation? Oh, check this out. It's a sixth order differential equation. Let me write it over here and write that in Leibniz notation. Of course, I've scrolled over that screen of the calculator and copy every single detail over to the slide. The point here is that we could find it is complicated differential equation using the P operator of Oliver Heaviside. That is a very powerful tool. We're not done. Tutorial time 3. But before that, observe. If we have KCL that we do, and we have KVL that we also do, and we have Ohm's law that we have reintroduced in its general form, we can use I have said. We can use, once we've replaced elements with impedances, we can use modified nodal analysis or any other circuit solution method. Let's do that. Tutorial time 3. The circuit is pretty much the first one we've seen, but this time I'll use M&A. How you remember? Reference node down here, node 1 up there. I'm going to find that current on the left-hand side, the current in the source. We've replaced the inductor and the capacitor by the impedances, and then we solve that using M&A. Branch currents, fine. Currents going in, one KCL equation, right? 10 minus V1 over the impedance 2 plus 2P. That's right, 10 minus V1 divided 2 plus 2P. That is equal to the current, let's say the current on the far right, that is V1 over 5, plus the current in the branch in the middle, V1 over that impedance. 3 in series with 1 over 3P. Fine, and then we solve that for V1. Solve that for V1? Yeah, in the calculator what I'm going to do is instead of writing V1, I will write X because it's the easiest it's the easiest variable to write. There is a letter key in the keyboard already, but to do that, I have to make sure that the independent variable is X, and you know how to do that. Mode CAS, independent variable, make sure that is X. I have written that KCL equation here, but instead of V1, I've written X. 10 minus X, X over 5, etc. Symbolic solver, and this one, this key F5, will solve for the independent variable. Which one? The one up here for X. Solve. Bang! That is actually V1, or rather, that is the differential equation whose solution would be the voltage of node 1. But that is not what we want, right? Let me clear the part on the left with CLQ, that one. That is V1. What I really want is this current. If I have V1, which is here on the screen, how can I find that current? You say easy. It is 10 minus V1, which is on the screen, divided by 2 plus 2P. Sure. 10, swap, subtract, 2 plus 2P, divide. That is the current. Evaluate to simplify that. That is the current, or rather, that is the differential equation whose solution is the current in the source. Let me copy that over here, and then we write it, expand it like so. We know that 240p is actually 0, and that is the differential equation whose solution is the current in the source, which is our goal for now. And now, what happens? Well, now that we have the differential equation whose solution is the voltage of the current that we want, we shall see how the equation itself in another video tells us a lot about the circuit behavior through some characteristics of that equation and of that circuit that we'll call the eigenvalues of the circuit. And in the end, in another video yet, we will see how to solve those differential equations. But to solve ordinary differential equations, we need initial conditions, which are, in electronic circuits, current in inductors at t equals 0 and voltage in capacitors at t equals 0. That is going to be our very next movie.
Well, now we know how to find the differential equation to solve for any voltage or any current in an electronic circuit that has capacitors or inductors. How? First, we replace every inductor and every capacitor by their impedance, LP 1 over CP. And then we apply M&A or any other circuit solution method of your choice and find that voltage or that current. What we get is not really the voltage or the current. What we get is an expression like this one, which is a differential equation that when we solve it, we get the voltage or the current of interest as a function of time. But you and I remember from our math courses that to solve the differential equation, we need initial conditions. Well, in an electronic circuit, the initial conditions are the voltage in every capacitor at t equals 0, and the current in every inductor at t equals 0. We will have another whole video just for that, initial conditions in electronic circuits. And then the video right after that explores how to solve those differential equations in detail. Until then, have a very good night, and thank you for joining me tonight.